okay? We would like to discover that. I would like to give you an A, which is a vector that will kind of estimate, in some sense, the theta value. The space is so big because you have capital M large there, and then this will be based on data. Okay, so the problem, as stated, is very simple. Of course, what I could always do to you is I could just toss coins and decide on the basis of the coin tosses what my action is. But you don't want to accept that. You say, I gave you this data, use this data to make this decision or this action. Okay? Now, so what happens? So we have the theta and we have the A. Then we have to ask the following question. If you know what theta is, let's say if you actually know what theta is, and I give you this action A, how are you going to assess whether this action is a good action or a bad action? How do you measure the distance between the true theta and the action that I had provided you? Okay? And so we get into the notion of losses. Okay? That's measuring how good the action is based on the theta that I'm giving you. So there are several possible actions losses that we could use here. One possibility here is simply what we call as the family-wise error indicator. Okay, and what is this? I call that as L sub 0. A, the action, theta, the parameter that is of interest. And what this simply indicates to us is that we made at least one false discovery. Why is that? Because remember, theta sub m is going to be 0 if there is no effect. And it's going to be 1 if it is actually relevant. A sub m is equal to 1 if you say discovery. And consequently, if theta sub m is equal to 0, this will be 1. If A sub m is equal to 1, then that means that you made a false discovery. If the sum of this is at least 0, or is greater than 0, then that means that you had made at least one false discovery. Okay? So that's what we call as the family-wise error indicator. But notice that if you have such a big number of decisions to make, maybe one false discovery is not too important. Okay? So we had changed that a little bit. We call that next loss as the false discovery proportion. What is that? Again, the numerator here, okay, it's like that one there. It is the total number of false discoveries that you had made by making the action A and the theta value is given. Okay? The denominator here is the total number of discoveries that you had declared. Like, for instance, I have the 40,000 genes. I'll say 1,000 of these are significant. Okay, that's the sum of the A's of M. And then, but out of those 1,000, I might have committed 100 false discoveries. In that situation, then, we would say that the proportion of false discoveries is going to be 100 out of 1,000. In the maximum, there is simply to remove the possibility of a 0 over 0, which we could just define as equal to 0. Okay? Now, so that's another one. Okay, false discovery proportion. And this is actually the one that will lead us to what we call as the false discovery rate, the one that was introduced by Benjamini and Hochberg, okay, which is a very popular measure of error now in this case. Now, these two types of errors, family-wise error in false discovery proportion, could be considered as type 1 errors. Type 1 errors are false discoveries, declaring that something is important when in reality it is not important. Okay? But there is another type of error that we need to be concerned about. It is declaring that something is not important when in reality it is important. That's what we refer to as the type 2 error. It's very possible, for instance, that there is a gene that is actually very relevant, but then I say, oh, that is not important. Now, why is that consequential? Maybe because I eliminated that gene for you, you might not be able to develop the appropriate drug to treat the disease. That could be a very bad error too. At the same time, a type 1 error where I declare to you that something is important, when in reality it is not important, could have very bad consequences also. You could be spending millions of dollars doing research on that particular gene, when in fact it is inconsequential. Of course, it's not the drug companies that will suffer. It is the people that buys the drugs because they will just increase the prices. But then you notice that there are consequences on all these types of errors. Okay, so the third type of error that I have here is what we refer to as the misdiscovery proportion. What is this? The total in the denominator is the total number that you ought to discover. That's the number of relevant genes, for instance. the total in the numerator is the number of non-discoveries that you had made. Okay? Because you notice that this will be 1 if theta sub m is 1, relevant, but then you declare am equals to 0 means not relevant. So if you take the sum of those, that is the number of false non-discoveries that you had made, and then you take the denominator there to be the total number of discoveries that you ought to consider. There are other types of type 2 errors that we could consider, like false non-discovery rates also are possible, but this is the one that I focus on in this situation. And this is what we refer to as a type 2 error. These two are what we refer to as type 1 errors, just like in the usual classical hypothesis testing where we only have one problem to decide on. Now, life would be very easy for us, okay? Of course, it would be very sad for statisticians if Paul, the oracle, is still alive. Okay, you know, Paul the oracle was the one who nearly caused a war between Spain and Germany, because Paul the oracle determined, in some sense, that Spain is going to win the game between Germany and that thing. So if Paul is alive, we could just simply ask Paul, okay, which genes here are important or not? Okay, so we wouldn't make any mistakes. By the way, Paul has died recently, so I say if only we still have Paul, okay, in that situation. Okay, now I say to that if Paul still exists, and we could ask an oracle about what the correct decisions are, then we would all be out of jobs because there will be no need for statisticians. Okay, so in some sense it's a good thing that we don't have oracles in some sense. Okay, but the idea is that we would like to be the oracles. In some sense, actually, we would like the statisticians to be the oracles in some sense, but with a certain chance that we are going to make mistakes. This is, by the way, the moment when Paul had chosen Spain over Germany. Okay, so I gave this talk one time and there was a German there in front. He said, I really love that, but it's kind of sad. Okay, so yeah, okay. So sadly or gladly then, we revert to being statisticians. And so the problem then is data is there to get discovered. I need to give you an A. So what do? We gather data, a big data usually, from microarrays, from Netflix, although the Netflix data is gone. I think they removed it from the internet. You know that Netflix data, there was a contest for $1 million to come up with a prediction tool. And I think somebody from a group from Stanford and Bell Labs and so on actually won the $1 million. And some statisticians actually were into that. Maybe they are not statisticians anymore. Maybe they had flown down to Miami and enjoyed the beach somehow. Okay, but you get this data. They took that out, by the way, because they said there is confidentiality issues, that somebody could pinpoint that Professor Duncan is actually the one watching all these movies and then you didn't get your consent. You know, earlier I had to sign a consent here that they could take my talk and put it in that camera and then put it on the internet. It's kind of scary these days because if you notice, they will put your evaluation ratings in the internet without your permission, and nobody complains about it. But so you didn't have to ask my permission to do this. Yes, but anyway, so you have this big data which I'll just call as X. Or X, there could be a very big data, millions of observations and so on. But statisticians or mathematicians will just call it X. It takes values in a certain space, which I'll call as script X, which we call as the sample space. Okay. Now, this data though, okay, one thing that we deal with in statistics, that we always deal with things that are probabilistic or random in nature. Okay, if I could have data that are, if that gene is, say, differentiated among the three groups, and every time I observe from group 1, I get a 0. Every time I observe from group 2, I get a 1. Every time I observe from group 3, I observe a 2, then there is no problem. I could immediately distinguish with one observation. But that's not the way it is, okay? Our data is always random, and it is following a certain probability measure or distribution. Okay, it's a cloud. Okay, you have these clouds. They could be clouds actually, but if they are very differentiated, then there is no problem. But the problem is that these probability distributions are intersecting in some sense, and consequently there are common points there, and we do not know what to do in those situations. Okay, so but you have this probability measure that governs this big data X. And now you could think of in that microarray data, for instance, remember I have rows, okay? I have rows. And I could think of X of M there as the data for the mth row. In this case, for instance, X of M will be the data from the 3 groups for the M gene. Okay? And it will be following a certain distribution, which I will simply call as PM. It could be, for instance, a multivariate normal, where you have independence among the 3 groups, okay? Or it could be binomials, okay? Bernoullis, for instance, okay? So for each XM, for each row, there is a distribution that is emanating from this big P, okay? So in that situation. Now, the thetas of M now, that was of interest to us, is nothing but a functional of that probability PM, okay? So if the PMs are identical for each of these groups, for instance, then I have theta equal to 0. If they are different, then I have theta equal to 1. Whatever you're trying to decide. So the thetas of M, the ones that we are trying to discover, are nothing but functions of that probability measure that is governing this theta X of M, so we have this situation. As an example, for instance, thetas of M could be equal to 1 if and only if the P sub M is normal whose mean is equal to 0, for instance, greater than or equal to 0, for instance. Then you say that is the discovery. Okay, otherwise you might say that that is equal to 0. So the pointer is that the thetas of M, the parameter that is of interest to us, is a functional of the probability measure that is governing the data that we are going to see. Okay, in the data is the kind of little things that we'll see there that tells us a little bit of what P is, inconsequently about what theta is. Okay, so you have that thing there. Now, next thing is what is a multiple decision function? A multiple decision function now is nothing but a function from that data space into the action space. Remember, the action space is the 0, 1 to the power M. That is the script U that I have there. This is the data space. This is where the data is residing. We'll see one of them. Okay, then based on that data, we would like to come up with an action, and that action is determined by this delta. Okay, so the delta then, because you have a total of capital M decisions, the delta then is going to be consisting of delta 1, delta 2, up to delta sub M. Now, what are these deltas? Those are the decision functions that you use for each of these decision problem. Okay? Now, you notice that I said delta sub M here is a function from script X into 0, 1. You might ask, are you allowing the possibility that the decision on the M gene is depending on all the other data, not only on the M data? And that is the possibility. And those are what we will call later as compound decision rules. Okay? So delta sub M is then this function for each of them, and so on. Now, you gather all this delta, you get what you call as the space of multiple decision functions. And the basic problem from a statistical point of view is to determine the delta that we will be using to choose that from this collection of possible decision functions. Okay, and if I have given you a choice, then if you get the data, you plug that into this decision function that will give you your action. Okay? Now, equivalently, the problem here, by the way, is this. I could gather the little m's where theta sub m are equal to 0. And I could gather for you the little m where theta sub m's are equal to 1. These are the relevant genes. These are the non-relevant genes. A lot of times, the cardinality of this is going to be small compared to capital M. But technically, this is the problem. What is script m sub 0 and what is script m sub 1? So you could put the problem in terms of deciding which of the sets there among the possible subsets is the one that is governing everything. Okay, so this is our problem. Now, another thing that I wanted to emphasize here is that in these types of problems, you could have dependencies on the data. It's very possible that when two genes are actually relevant, then the data that you are seeing from them are going to be correlated or associated. But when the genes are not relevant,